a long journey for Diego. Welcome to you all. Diego did his bachelor's in electrical engineering in the University of La Salle in Bogota in Colombia, and then followed that with a degree of computer engineering at the University of Los Andes in also in Bogota. His master's was on 3D MR image analysis, so he's continuing on the theme. After he left Colombia, he went to the land, one of the lands down under, Australia, to Brisbane, to the CSIRO eHealth project. When he was in Australia, he would say things like, "G'day, mate. I'll have a flat white, please." But he also joined the team there in Brisbane, looking at MR imaging for Alzheimer's disease, and worked a lot with the Creatus group at the University of Lyon in France. He also had a lot of experience in industry with many positions in business, government, education, working on all sorts of projects from small scale to fairly large scale systems. So when he came to robots, he brought a lot of that experience both from the medical image processing side and the sort of pure fundamental IT side. While he was here in the middle of his PhD thesis, he managed to also write the first textbook on WebGL, a new environment for working with the web and cloud computing. And this book has already been translated into Chinese and Korean. I think he gets a much larger, he's probably had a much larger revenue stream from that book than I have ever had in any books that I've associated with. The application of this stuff was so fascinating that we were looking for a while to see if we could find a way to integrate that stuff into his thesis. At some point, I think it was always on the verge of taking over his thesis. But anyway, the clinical focus prevailed in the end, so he's now going to talk to us about multivariate analysis of MR images for temporal lobe.
Well, thank you for that introduction. So, I would like to start my talk today with a personal story. In 2005, my brother and I were staying with my grandparents for a weekend. We were sharing a bunk bed. And I remember I had to go to bed early because I had a very important exam that Monday morning. So around 2 a.m., I heard this very loud rattling noise that woke me up. And I thought, well, probably my brother is just trying to fall back to sleep, but the noise wouldn't stop. So I reached out to see what was going on. And then that's when I noticed. My brother was staring into the void. He was clenching his fist like this. He was grinding his teeth. And he was trying to control this infinite loop, this jerking motion that wouldn't go away. Well, he was having a seizure. And I knew it was a seizure, but I had never seen one. So it took me completely by surprise, and I recoiled. My grandmother came along, and then she called an ambulance, and then we stood there completely powerless without being able to help him. After a few minutes, when the seizure stopped, my brother was disoriented. He was extremely tired and very sad. Temporal lobe epilepsy is a disease, or TLE, is a disease characterized by seizures that originate in the temporal lobe. It's the most common type of focal epilepsy, accounting for 60% of epilepsy cases. The origin of the disease is multifactorial, and it includes tumors, vascular and developmental malformations, hereditary conditions, among others. Now, there are two types of TLE, mesial, and this is when internal structures in your temporal lobe are involved in seizure, and then lateral, and this is where seizures are more superficial, occurring in the neocortex. The most common type of pathology is mesial temporal sclerosis, or MTS, And this is a pathology that is characterized by neuronal loss in the hippocampus, and it's commonly visible under MRI. The current treatment for TLE consists of anti-epileptic drugs. And in most cases, these drugs work, but in about 30% of the cases, the patients become drug resistant, and then they require surgery. Now, surgery is really invasive because they have to take out part of your brain, part of the temporal lobe. Okay. So, in the weeks following my brother's seizure, he received an electroencephalogram, and this is when they put electrodes on your scalp, trying to measure abnormal electrical activity. And also he received an MRI. And when my family got the results, it was a bittersweet moment. It was sweet because, well, they didn't find anything. But it was bitter because, well, they didn't find anything. So we were left without knowing what had caused the seizure. And I want to make the point here that this is a very common scenario. And in fact, the sensitivity of EEG is of about 70% or less. Whereas MRI is a little bit better than that, but still you require to have lesions that are clear enough, they have enough contrast, and they have an adequate size to be detected. So this raises the question, what can we do to improve MRI-based diagnosis of TLE? So let's take a look at what we have here. Current clinical MRI. In current clinical MRI, visual cues for TLE diagnosis can be ambiguous. You see, diagnosis depends on contrast, and contrast depends on the specific acquisition parameters that we have. Now, the alternative that I'm going to present today is quantitative MRI. And in quantitative MRI, voxel intensities reflect intrinsic tissue properties that don't depend on the contrast. Specifically, I'm going to discuss two types of quantitative MRI. One is quantitative relaxometry, and the other diffusion tensor imaging. So with quantitative relaxometry, we measure the T1 and T2 properties in tissue. These properties characterize magnetic relaxation in the time domain. T1 describes the longitudinal magnetization recovery, which is an exponential process. And T2 characterizes the transverse magnetization decay, which is also an exponential process. So to obtain these two maps, we are going to acquire a set of T1 weighted and T2 weighted images respectively, and we're going to use these images to take these exponential curves. Now, DTI, or diffusion tensor imaging, is another quantitative technique that probes the microstructure of tissue by measuring the degree and the direction of water diffusivity on every voxel. So for time points A and B, when diffusion is restricted, we will obtain the same signal. And when diffusion is not restricted, then we're going to observe a signal drop in time point B. Now, by measuring diffusion in many different orientations, we can come up with a three-dimensional model of diffusion, and that's what we call the tensor. And from this tensor, we're going to derive two measurements. FA, or fractional isotropy, give us an idea of the preferential orientation of diffusion. So if diffusivity occurs in all possible directions in the same manner, then the tensor will look like a sphere. But if there is a preferential orientation, then the tensor is going to look like an ellipsoid. On the other hand, we have mean diffusivity. And with mean diffusivity, we're going to look at the amount of diffusion, regardless of the orientation, the preferential orientation. Now, why are we using quantitative MRI? Well, the reason for this is that there is a strong correlation between what the measurements that we obtain in MRI with internal changes in the tissue, with micro changes in the tissue. So our measurements have a good diagnostic value. All right, so in summary, the purpose of my talk is to investigate the use of quantitative MRI in the diagnosis of temporal lobe epilepsy. My specific objectives are, first, I want to explore mechanisms to integrate quantitative MRI in a diagnostic application. Second, I want to measure the individual contributions of both quantitative relaxometry and diffusion tensor imaging. Third, I want to look at specific patient subpopulations. I want to look at patients who have MTS and patients who don't have MTS. Similarly, I also want to look at patients with left temporal lobe epilepsy and patients with right temporal lobe epilepsy. And finally, this is because I'm a software engineer, I want to look at how I can automate this process with machine learning techniques. Okay. The challenge is that I have a relatively small sample, and this has to do with the fact that the disease is so heterogeneous, right? So this makes my sample relatively small. So how I'm going to approach this problem, I'm going to do it in 3 parts, and this is going to be the bulk of my presentation today. On the first part, I'm going to examine patterns of abnormality that are individual. So I'm going to take one patient, and I'm going to compare this patient with respect to my control group using quantitative MRI features. Okay? In the second part, I'm going to introduce machine learning, and I'm going to show how we can automate the diagnosis with quantitative MRI features. And in the third part, I'm going to be looking specifically at the asymmetry in the temporal lobe, and I'm going to show how this allows us to have a better sensitivity for the detection of TLE. All right. So this is the first part. So the motivation for this part is, okay, I have one patient and I have a group of controls, and I want to see how different the patient is from that control group. So to do this, I'm going to start with the T1 map here. And also my images are already co-registered, so they are in the same space. So I take the T1 map, and then from this map, I'm going to obtain a T1 weighted map. And the reason for doing this is that the segmentation algorithm requires contrast. Like many segmentation algorithms require contrast. And the T1 map, as I mentioned before, as is the case for the other quantitative maps, they don't provide sufficient contrast because they are not based on contrast. So I need to do this transformation. I use the honest method to generate the T1 weighted map. And then I'm going to use an anatomical atlas to do the segmentation on the T1 weighted. And then this segmentation is going to be propagated to the other images. So this is the atlas that I use. This atlas has a parcellation of the cortex, as you can see here. Also, we have different regions in the white matter, and we also have internal structures here, like the cutaneous, for instance. So this is a very slow process. It's very complicated, and it takes around 1 day. Now, once that process has finished, then we're going to extract features. So here, for instance, we have the left and right hippocampus, and we are going to measure the left mean intensity of this region, the right mean intensity, and I'm going to compare both regions in intensity and in volume. So in volume, I just measure the 2 volumes, subtract them, and then measure the absolute value of this subtraction. And for intensity, I'm going to look at the distribution of signal in both regions. So for the same example, I have here the left hippocampus in green and the right hippocampus in blue, and you can see that they don't overlap. So to measure the asymmetry, in this case, I'm using a Kolmogorov-Smirnov test that takes the cumulative distributions of these 2 distributions and measures the maximum distance. So for a control, there is generally a better overlap, as you can see here, and then the distance between the cumulative distributions is minimal. But for our patient, as you can see here, the distance between the cumulative distribution is larger than here. Okay, so these are the features that I'm extracting: mean intensities and asymmetry in volume and in signal. And with that, I'm going to do a single subject t-test. So I'm going to take my patient, and I'm going to compare this patient in those features with respect to the same features in the control group, as you can see here. And I'm going to divide my results in 4 what I call individual maps. So I have the right map. So this right map is going to show me the abnormalities in the right hemisphere by doing this comparison. Similarly, I have the left map here. And here, I'm going to measure the asymmetry in volume first, and that asymmetry is going to be compared to the existing asymmetry in the control group. And I do the same for intensity. Okay. In addition to this, I'm going to use the intensity asymmetry map to try to lateralize my patient. So remember that we have people with left TLE and people with right TLE. So by measuring how many instances of asymmetry you have in the temporal lobe, how many significant differences there are, then we can calculate laterality score. For the left people, it's usually negative, and for the right group of people, the patients are usually positive. Okay? So let's take a look at some results. Right. So this is a patient with MTS. And as you can see here, in all these maps, you can see that the hippocampus is heavily involved, and there are not other regions except by this urinary volume. But the common thing here is that the hippocampus is involved. And we know from the clinical diagnosis that this patient is MTS, so our method is able to detect the hippocampal involvement. Similarly, when you measure the asymmetry in intensity, for this particular patient, it came with, the result was a -1, so the method correctly classified this patient as a left TLE patient. Okay? Similarly, for a non-MTS case, here in the maps you don't see here any hippocampal involvement, and you can see that both in the left hemisphere and in the right hemisphere, we have abnormalities. Okay? And this makes sense with the clinical presentation for this patient. And actually, this patient, when they took the EEG, they found bilateral spikes in both hemispheres. So this kind of corresponds to that clinical presentation. Now, when we look at the symmetry with the symmetry map, the laterality score in this patient gave us a +1. So this patient was correctly classified as a right TLE patient. Now, I cannot show you all the patients because we won't be out of here in time, but I can show you some results when we look at all the individual results. So here, I have divided the abnormalities per region of interest, and here we have the frequency. So we showed that in the limbic system here, there are statistically significant differences between the MTS group and the control group. And this has previously been reported by other research groups. But more interestingly, we found a statistical difference between controls and the non-MTS group. And this is really important because the non-MTS group is the most difficult to identify. So there has been some previous results on this, but this result, it confirms the previous suspicions that we had before about the MTS group having more differences in the cortex. All right, now, if I show you the same results, but in this slide, organized by imaging, by type of image, so I have T1, T2, FA, and B. On this plot, I have the mean intensities, and on this plot, I have the asymmetries, okay? So I want to call your attention to this pattern here of ipsilateral decrease in FA and ipsilateral increase in B. Both in the MTS positive group. So this is something that also has been previously reported in the literature. So our results confirm previous studies. More interestingly, we obtained significant results in the quantification of T1 differences between the MTS group and the control group. And this is something really novel. This is something that our research group is innovating. Also, another interesting result is that here we observe a pattern of increasing asymmetry between the control group, the MTS negative, and the MTS positive group. So this is also something novel. All right, so in general, we observed that all the patients with MTS were correctly identified in these maps. And with the laterality score, we were able to identify left and right patients in an 80%, with 80% of accuracy. As I mentioned before, the MTS negative group is more difficult to diagnose. And when we measured that statistical difference, we observed that most of that difference came from the MD signal, from the mean diffusivity signal. So this warrants further research on this area for the MTS. The contribution of this part is the development or an individual patient diagnostic analysis. We confirmed the results with the literature, and we integrated volumes and regions of interest. We are pioneering in T1 quantification, and we analyze the relative contributions of quantitative relaxometry and DPI. And this has been submitted for publication to the International Journal of Computer-Assisted Radiology and Surgery. All right. So this is the second part. And I'm going to talk here about machine learning. So the motivation for this is, okay, we have all these patterns, but how can we train a physician to know these patterns and to do the diagnosis based on these patterns? So that would take way too long. And I'm a software engineer, so I, of course, look for an automated method. And machine learning is all about recognizing patterns, so it seems like a perfect fit. So, and this part, I would like to tell the story. This happened last winter. I was driving with Jose. Where's Jose? Hi, Jose. We were driving. We were going on a weekend getaway, and then, as good Colombians that we are, we never check the weather because we don't have snow in Colombia. So we just left, and then we ended up driving in the whiteout conditions, and there were some times where you could see the road, and there were some other times where you couldn't see anything, right? So I thought, well, this is a very interesting example of feature recognition and pattern recognition as well. So on the left, you can see it's much easier. You can see the energy post, the oncoming traffic, the lane divisions, and the tree line, right? But can you tell me if you can distinguish the same features on the right? So please raise your hand. You can see the truck. That's not too bad. All right. What about the tree? Can you see the tree? Good. Good, good. What about the lane division? Okay. So let's take a look. So this is the lane. Okay. This is the tree. And this is the truck. Okay. So to perform this task safely, we need to identify good features. Okay. And with those features, we are going to construct a feature vector. Okay. However, not everybody is good at recognizing good features, and this is why accident happens. And there are many reasons why an accident could happen. But training can help in those situations. And when you have training, something very beautiful happens. In the case of medical imaging, we have different specialties. So pathologists are very good at recognizing patterns in 2D. Also radiologists. And surgeons are more familiar nowadays with 3D patterns. Okay? But what happens when you have more than 3 dimensions? So this is what I believe that machine learning can help us. Okay. So how do we do machine learning in medical imaging? Well, first of all, we need to acquire our images. We need to extract features and identify good features. And then we're going to train the machine, and then we're going to ask the machine for the diagnosis. This is basically what we do. So I already showed you the images that we're acquiring. Now let's talk about extracting features. So say, for instance, that this is a dynamic CT. So every frame here represents the heart in a different cardiac, part of the cardiac cycle. So if we wanted to extract a feature vector from a dynamic CT, then we would extract features from every frame, and then we put them in the feature vector. In our particular case, what we want to do is we want to take these measurements, these features from the regions of interest that I showed you before, and we're going to extract features from the 4 images, from T1, T2, MD, and MFA, and that's the way we're going to construct our feature vector. All right. The second step is to identify good features, okay? So say, for instance, that in this slide, the color of the feature represents its value. So according to that, these would be good features, right? Because the color or the value allow us to distinguish between the 2 groups that we want to identify. But there are going to be some cases where the feature is missing. you see here is missing and here is missing. And even in those cases, we can still perform a good job with this feature. Now, there are some other cases where features don't have enough variability, so they kind of look like we can distinguish the two groups, but not really. Or cases where they are completely oblivious to the groups and there is no variability, right? So I'm going to show you, well, okay, when we do this, we can pass from millions of features to hundreds of thousands by doing feature selection. I'm going to show you a couple of techniques to do feature selection. So the first one is based on correlation. And in this feature, we're going to measure two different correlation coefficients. The first one is going to measure the correlation of the feature with the group. So say that this is -1 and this is +1. You measure the correlation and then you see if the feature discriminates the group or not. So that's the first step. And this is what corresponds to the maximum relevance. Okay? Now after doing that, you have selected a bunch of features and then you measure the correlation between them. So if they are highly correlated between them, then that corresponds to the redundancy part, and this is the part that you want to minimize. So graphically, this is a feature that has a very poor correlation, and this is a feature that has good correlation. And what you see here is if you have features that are highly correlated, then you eliminate one of them, and then that way you make it, you minimize the redundancy. Okay, there is another method that I'm going to show you today, and this is the ANOVA-based feature selection. So basically what you do is an ANOVA test on this feature, having these two groups, all right? And in this case, what you want to do is you want to measure the within group variance with respect to the between group variance. So when the within group variance is larger than the between group variance, then the data points are completely mixed into each other like you see here. But when the opposite happens, then you see that two groups form. And these are kind of features that allow us to distinguish between those groups. Right. So say that you have done feature selection and then you plot them and then you see that all the information lies on one particular feature. Well, if that's the case, then we can safely remove these other features without losing generality because there is not much variance, therefore we can get away with it. But this scenario really rarely happens, okay? A more general scenario is to have something like this, where the variance in our data has a preferential orientation. So in this case, PCA allows us to rotate the axis along the maximum variance of our data, and then we can repeat the same exercise and remove those uninteresting components in this case, okay? So when we combine feature selection and PCA, we can go from millions of features to just 10 or 5 or 3. It depends on how many components we want to keep at the end, all right? Now let me tell you a little bit about, okay, we have extracted features, selected good features, we have reduced the dimensionality with PCA. The next step is to do the training and the testing, okay? So in training, we use those features in that reduced feature space to train the machine. So the training basically is the obtention of a decision boundary as you see here, okay? This is what we do with training. Now, for the testing, we're going to present a subject that wasn't used for training and therefore didn't have anything to do with the calculation of this decision boundary. And then we're going to ask the machine for a prediction. So the way it works is we take these features and then we see where that subject lands. If it lands on the right or on the left, then we call it a patient or a control. All right? So now I want to do a little experiment because I want to test your decision boundary. Okay? So I need some teamwork here. So the challenge is to recognize the sharp S sound in German. All right? So this word, does anyone speak German? Do you want to participate? Yeah? Do you know how to pronounce this? Straße. Okay. You want to come here? No. Okay, so we have two sounds here. We have a soft F, we have a sh, right? And then we have the sharp S, which is S. So if I gave you something like this, it would be very difficult for you to tell me, okay, the sharp S sound is right here. Okay, so what I'm going to give you is I'm going to give you some features. All right? I'm going to transform this and give you some features. So this is transformation. So here we have a spectrogram. It contains the same information as the wave that we saw before, but we have information about the different frequencies in time. So the other piece of information I'm going to give you is this. So the sharp S sound is most similar to the sound in English, and that looks in a spectrogram like this. So you can see that the sharp S sound has a high frequency component and a very low, there is more energy in the high spectrum than in the low spectrum. So that's the way you can distinguish it visually. Okay? And if this is working, I'm going to play you the sound.
Straße,
Can you hear it? Let's do it one more time.
Straße,
Okay, so I gave you a feature, I gave you two features, the sound and the visual cue, okay? And now what I want you to do is I want you to, okay, first of all, are you ready? Good. So I want you to tell me how many times the sound appears in this chorale, all right? So some of you already are counting here, but let's play it, okay? All right. How many times? Okay, Jackie, how many times?
6
All
sharp,
right.
I would say,
Okay.
and then a few softer S's.
Okay. Golafson, how many times? Give me a number. Come on. Give me a number.
7.
Who says 5? Raise your hand. You think it's 5. Okay. Have 2. Raise your hand. You think it's 7. Okay. Raise your hand. Is it 6? Okay. So it's kind of like a tie. Okay. So we have. Sorry, I have to do this instead. We have 6 times. Okay. And I'm showing you here where they are. And let's play one more time. You can compare.